Okay. All right. Let us continue. And today also is the final talk of Professor Etingof.
Okay. Thank you for everybody for coming back. So I learned from Sam that I should say this. Okay, so today we'll finally talk about quantum Hitchin systems. And before I start, I should talk about what does it mean to quantize, what is a quantum integrable system? And what does it mean to quantize a classical integrable system? Well, first of all, this is not even the most basic question. There is a question that goes before that, because an integrable, classical integrable system lives on what? It lives on symplectic manifold. So we should first say what it means to quantize a symplectic manifold. So integrable systems live on symplectic manifolds. So what does it mean to quantize one? So I'm going to be rather sloppy about what kind of function. So this story can be told in the setting of smooth real manifolds or complex analytic manifolds or algebraic varieties over an arbitrary field, even over a positive characteristic. But I'm going to be sloppy because I'm just explaining motivation. So suppose M is a symplectic manifold. So in this case, functions on M form a Poisson algebra. And in the case when this is algebraic variety, a complex manifold, which is not affine or Stein, then you may have to consider sheaves of algebra. So this means that given two functions, f and g in here, we can attach to it Poisson bracket fg, which is a Lie algebra structure, and also it is a derivation with respect to each argument. And then quantization of M well, this is M is called well, in classical mechanics, M is going to be a phase space of some Hamiltonian system, and O of M is a space of observables, classical observables, algebra of observables. And the quantization of M means that we are going to replace observables by operators, which first of all means that they will still form an algebra, but they won't commute anymore. So this means that we define some algebra A over, well, let's say, formal power series of H, or maybe polynomials of H, which is non-commutative. And which is, so it has a multiplication law. And quotient is isomorphic to O of M. And also the limit of f star g. So this means that we can think of it, so it should be a flat module over polynomials in H or formal series in H. So this means that we really should think about the same space tensored with polynomials in H or series in H. And multiplication is given by some star product, but it's not commutative. However, the commutator is 0 modulo H. And if I divide it by H, then this is going to be the Poisson bracket. So I'm being very sloppy about this. And there is a big theory here that a separate course could be dedicated to, but I just giving it for the purposes of motivation. So that's what I mean by symplectic manifold, by quantization of symplectic manifold. And an example of this is, so if M is a cotangent bundle of another manifold Y, then there is a very simple way to quantize it. So then the natural quantization is the algebra of differential operators on Y. More precisely, so let me call this algebra D of Y. More precisely, well, it should have a parameter H. Well, subalgebra dH of Y generated locally by coordinates and H times the derivatives with respect to these coordinates. So this corresponds to the classical yoga for, standard yoga of quantization and quantum mechanics when we replace momentum variables. So functions, so let's recall that functions on T star Y locally are generated by coordinates and momenta. And the yoga of quantization is that we replace momenta by quantum momenta, which is this pi hat, and the commutator of pi hat with xi is h bar, which is the Heisenberg uncertainty relation. There are, in the actual physics, there are square roots of -1 in these formulas, but for my purposes, it's not going to matter. So essentially, this means that quantization, you can, in this situation, you can rescale this h bar to be 1. And so the actual upshot of this discussion that quantization of functions on the cotangent bundle should be the algebra of differential operators. So now I want to say what is an integrable system. Well, classically, this means that I have some, so suppose dimension of y equals n, and so I have some functions h1 through hn on T star y, which Poisson commute, they're in involution, and they are functionally independent. But in algebraic geometry, actually, we should say algebraically independent. So, so this defines as a map from P, from cotangent bundle of Y to the n-dimensional space. So let's, in algebraic category, I would write it this way. And algebraically, this corresponds to the pullback map between functions on this affine space, which is just polynomials let's say, of some variables, x1, xn, it should map into functions on t star y. And xi under this map goes to the integral hi. And this map should be injective. This corresponds to the fact that these functions are functionally independent or algebraically independent. And also it should be a Poisson commutative subalgebra. So that's what an algebraist would say, what it means to have an integrable system. And for an algebraic geometry, this is what an integrable system is. It's a commutative subalgebra inside here, and there is a standard theorem that any function Poisson commuting with this integrable system is algebraically dependent on them. So in a sense, this is maximal, at least locally. Or maximal in algebraic geometry up to taking a finite algebraic extension. Taking an algebraic extension. Yes? That's right. Yes, it is the same as to have an integrable system or Poisson commutative subalgebra. So if you want to, okay, the subalgebra doesn't have to be a polynomial algebra, but there are always nice polynomial algebra inside any finitely generated commutative algebra by Noether's normalization lemma, such that the full algebra is a finite module over this polynomial algebra. And so there are, basically it's equivalent to talk about commutative Poisson commutative subalgebras and functions on T star y is the same thing, which are maximal in this sense. So which means that they have transcendence degree. So maybe I should write this. So if y is a smooth algebraic variety, then classical integrable systems on T star y correspond to commutative subalgebras, Poisson commutative subalgebras, in functions on T star y of transcendence degree equal to dimension of 1. Or Krull dimension equal dimension of y, if you're talking about finite dimension. But in any case, so quantization of this well, functions on T star y in the quantum picture is replaced by non-commutative algebra A. So this means, suppose A is a non-commutative algebra quantizing T star y, which is a Poisson algebra. And then we have some polynomial algebra, C of x1, xn, inside A. Well, this was Poisson commutative, and Poisson bracket is the first approximation to the actual commutator, fg minus gf. So we should say that this is just an ordinary commutative subalgebra. And so in this case, this would be differential operators on y, if we have started with O of T star y. And actually, there is a similar theorem here, which is due to Makar-Limanov. So if so this xi go to some operators hi and here. And if h commutes with hi equals 0, and h belongs to differential operators on y, then h is algebraically dependent on h1, h, where dimension of y equals to n. Okay, so this is just a background. So if you want to quantize and construct a quantum integrable system or quantize an integrable, if you want to construct a quantum integrable system, so to construct a quantum integrable system, need a big enough commutative subalgebra, or if you like to say maximal, up to algebraic extensions, commutative subalgebra in the algebra of differential operators on y. And then we will say that it's a quantization of the classical system if it converges to it when h bar goes to 0. This quantizes a classical integrable system if it converges to it when h bar goes to 0. And but when h bar goes to 0, this means that we should replace this pi hat with commutative momenta pi. Not by 0, but by the commutative momenta pi. So this is just the general yoga of quantization, symplectic manifolds, cotangent bundles, and integrable systems. It's just a review. So now we want to apply this to our situation. Okay, so first of all, so this gives rise to a naive quantization procedure. Just stick h bar times d sub I, where you had pi. And well, this is clearly not a good thing to do in general, because there will be ordering problems, because this di do not commute with coordinates. So if you have something like xi times pi, then there is a question, where should it go? To xi times di or to di xi, which differs from this by h bar. So there is an ambiguity, ordering ambiguity. And so that means that in many cases this is going to fail. But it does succeed sometimes. So it's actually the first example that we considered last time, which is the Garnier system, is nice enough that this stupid procedure does produce a quantization. So, so remember the Garnier system, which was deformed, had the following Hamiltonian HI, or maybe GI, they were called. And this is the sum over J different from I. Well, we had the coordinates were called Y, but okay, let me call them X now. So, so there was this PI, PJ, plus XI minus XJ, lambda I, well, twice lambda I PJ minus lambda J PI plus twice lambda I lambda J divided by Ti minus Tj, where x's and p's are the standard coordinates in momentum. And so then we can replace it with gi hat and just replace the pi's with ih times dxi. So we've got xi minus xj squared h squared di dj plus twice h xi minus xj lambda I pj minus lambda j pi plus twice lambda I lambda j over ti minus tj. And so these things, so I can, actually it's convenient to divide by h squared. And then I'm going to obtain, so this h squared is going to go away. This h going to go away and will be in the denominator here. And finally, here, it will be like this. So, it's convenient to introduce capital lambda I, which is twice lower lambda I times h over h. And so this is going to be the sum of minus xi minus xj squared di dj plus xi minus xj times lambda I p d. Lambda I dj minus lambda j di and plus 1/2 of lambda I lambda j. And this is divided by ti minus tj. And this is the so-called Gaudin system. For PGL2. And you may have seen it in representation theory, but maybe you won't recognize it because representation theorists write it in a little bit different way. So let me explain it. So actually, a representation theoretic way of writing it. Well, for that I should recall the action of SL2 by differential operators. Let's say enveloping algebra of SL2 on differential operators on the line. So this is a well-known action, which sends, so let's recall that SL2 is generated by E, F, and H with the standard relations. And then E, so F goes to minus dx, H goes to twice x dx, and E goes to x squared dx plus 2, so here is going to be plus lambda, and here is going to be plus lambda x. So this is actually action on the line, but it extends to action on projective line, except that then it maps to twisted differential operators, which act on sections of some lambda's power of the bundle O of 1, if lambda is an integer. Okay, and so then we have the Casimir tensor, omega, which is, this lies in, so let's call this G, so in G tensor G. And it's given by the formula E tensor F plus F tensor E plus a half of H tensor H. And this is the unique up to scaling invariant element in here. In fact, it lies in the symmetric square. And then this thing in the numerator for GI hat is just, so numerators are just, you can observe that this is just omega ij. So this means that omega acting on the ith variable and the jth variable. So that's an easy exercise to check for lambda equal, for parameters lambda I. And so therefore this gi hat can simply be written in the following way: the sum over j not equal I, omega ij divided by ti minus tj. So it's a very simple formula. And now we have a formula that omega 1, 2 with omega 1, 3 plus omega 2, 3 is 0. So, and from this, it is easy to deduce as an exercise that these g's commute. And note that this is, in fact, true for any simple Lie algebra G. So we should think of these operators as elements of enveloping algebra of G to the power n. And this is true for any simple or semi-simple Lie algebra G, because all it uses is that this thing is invariant. And therefore, this is also true for any Lie algebra. So we do get a commuting system of operators for any Lie algebra. Well, they are not quite operators. They are elements of the enveloping algebra to the n. But we can make them into operators by making them act on representations. So I claim that if you have formal letters omega ij which satisfies such condition, then these things for arbitrary complex numbers ti and tj will commute. And this is very easy to check by direct computation. And so these are the Gaudin Hamiltonians for G. More precisely, well, in quantum mechanics, we want to have operators on a certain space. So, so we should take some representation. So if V1, Vn are representations of SL2, of G actually, then this Gi hat becomes operators on the tensor product Vn, which commute with G. And in particular, they act on the invariance. And so it is looking at this invariance that is analogous to the story we did yesterday, because there we took a quotient by the diagonal action of G. But you can also consider them without invariance. And so we'll get interesting families of commuting operators in this way. Well, for Lie algebras of higher rank, this is not going to be a quantum integrable system, because we know that in that case we also have to consider higher order. So this only comes from trace phi squared, but there we will have to consider higher order operators, which I didn't write. But in any case, so the upshot of this is to this kind of trivial procedure of sticking in derivatives instead of momenta works perfectly fine in this example. But this is an exception rather than a rule. Of course, these ordering problems will arise as long as you consider something more complicated. So here is another example we also considered yesterday where this is going to fail, or more precisely, it will succeed for the quadratic Hamiltonian, but it will fail to provide a proof of integrability, of quantum integrability. So the next example is the elliptic Calogero-Moser system, but actually the same applies to rational or trigonometric Calogero-Moser, which are limits of this. So, so let's recall that the classical Hamiltonian H2 of this system is the sum over I of pi squared minus, let's say, sum over j different from I, p function of qi minus qj. There is some coefficient here, but it can be rescaled, so yeah, I'm just putting 1. So this is the classical Hamiltonian, and so we should quantize it. So h2 hat, and then also I should divide it by h squared. So I should replace this by h squared dxi squared, and then divide by h squared. So I will obtain that the sum over I of di squared minus 1 over h squared, sum over j different from I, p function of qi minus qj. So that's a nice thing. It's a differential operator of second order. And in fact, it is the right operator. So this constant no longer can be rescaled, so I'm not going to remove it. And the theorem indeed is that this defines a quantum integrable system, which is just the centralizer of h2 hat in the differential operators in n variables, but it doesn't follow, it does not follow from the classical one. And the reason is the following, that, I mean, it doesn't immediately follow. So you can actually, if you play around, you will figure out the correct orderings in this case. But in more complicated cases, it's not going to follow. So, and the reason is the following, that suppose you want to look at the H3 Hamiltonian. So I gave yesterday a problem of computing this Hamiltonian. So it has the form sum of pi cubed plus sum of pi times functions of q, and plus another function of q. And I'm not going to tell you these functions for two reasons. One is not important, and the other, you still have to do the exercise. So, but in any case, it has this form, and you see that already here, you're going to get this ordering problem. Do you put di on the left of this function, or on the right of this function, or some mixture of that? That will already affect the answer, and so there is no simple answer to this, and so that's why. So pi times fi of q should go to di fi of q, or fi of q times di, or something else. So this shows that we need some more systematic approach, and in fact there is no general approach. You really have to work. There is no general way of quantizing an integrable system. You just need to go back to its definition, to the definition of the classical system, and see if you can change the way you obtained it. And that's what we are going to do. By the way, so we will succeed with the quantum Hitchin system thanks to the work of Beilinson and Drinfeld, which is quite deep, in fact. And in particular, in the case of SL2 with parabolic structures in genus 0, we will obtain this. And in the case of arbitrary group with parabolic structures in genus 0, we will obtain these Gaudin Hamiltonians as a part of the Hitchin system. But there will also be other Hamiltonians that commute with them which have more complicated structure and which have higher. So these are second order differential operators, but they will higher order differential operators. Okay, so so for this purpose, I need to recall the construction of the Hitchin system. And for this, we need to recall the double quotient construction of the bond G of X, which we used for that. So bond G of okay, so recall how we constructed. So how we constructed the Hitchin system. So there was two steps. Step one was represent bond G. So this was a system on bond G of X. Well, some open set, but never mind, that's not important. So first we represent bond G of X as a double quotient. And second, so the double quotient was in the case of one puncture of this form. And step two, we constructed some commuting Hamiltonians on cotangent bundle of this infinite dimensional group G of K, which are invariant under both actions, invariant under left and right action of G of K. So recall that these Hamiltonians depended only on the Higgs field phi. So if we trivialize the cotangent bundle using left translations, this means that it is left invariant, but also they were given by some conjugation invariant functions of phi, which means that it is also right invariant. And then we descended them to the Hamiltonian reduction by the group G of X minus X acting on the left and G of O acting on the right to get to a system in T star bond G of X and obtained the Hitchin system. So what happened is we had infinitely many integrals here. They become heavily linearly dependent, but what remained still formed an integrable system on this finite dimensional space now. So we need to try to retrace our steps here. And the first thing we need to do is we need to discuss what is quantum Hamiltonian reduction, because that's the procedure we used before. So quantum Hamiltonian reduction and let me right away do it along an orbit. So classically, we have some group H acting on some symplectic manifold M. And we have a moment map, which is a piece of data from M to the dual space of H. And then we have an orbit inside here. And then we take, so Hamiltonian reduction is preimage of O modulo H, which will be a symplectic manifold in nice cases. So if the action is nice. So what should we do quantum mechanically? We should understand what are the quantum analogs of these things. So first, H should act on a quantization of this symplectic manifold. So this means H acts on some algebra A, which is a non-commutative algebra. And then we should generalize what moment map is. This moment map is Poisson. So this means that we can think about it as a map of function algebras the other direction, which is an homomorphism of Poisson algebras, functions on H dual into functions on M. And if we are talking about polynomial functions, this is just the symmetric algebra of our Lie algebra H. This has a natural Poisson bracket, which is a Kirillov-Kostin bracket. And this is a Poisson homomorphism. So when we quantize, Poisson homomorphisms between Poisson algebras should become ordinary homomorphisms between non-commutative algebras. Now, quantization of symmetric algebra of H is just the enveloping algebra of H. So this quantum moment map should be a map from enveloping algebra of H into A. So this is a quantum moment map. And this is a piece of data that we should be given. So now we have to build this quotient. And so what is the analog of movement to the -1 of O? That's actually a sticking point because mu-1 of O is not a Poisson submanifold. It doesn't have a Poisson structure. And for that reason, we cannot quantize it to an algebra. So it's actually more convenient to say that mu inverse of O over H is contained inside inside M over H. It's cut out by the equation that mu of M equals 0. This equation makes perfect sense because it is H invariant. And so this thing we can quantize because functions on M over H is just invariant functions under H on M, which is a Poisson subalgebra of O of M. And then this procedure, so O of mu inverse of O over H is the quotient of O of M over H, which is O of M H, by ideal of equation mu inverse mu of M equals 0. So this is good because this is something that we can say in the quantum world. This is all classically, but I'm writing. So this is the data in the quantum theory, and then I need to understand what to do with this data. So I go back to the classical case and look at what we have there, and I translated it into a language that I can now extend to the quantum case. So definition. The quantum Hamiltonian reduction of A by H is the algebra in invariance H invariance in A modulo H invariance in A times mu of the Lie algebra. And so this is an ideal. So A times mu of H is only a left ideal in A, but you can check that after taking invariance is a two-sided ideal. In A H. And also, if H is reductive, which won't be the case here, but if H is reductive, this is the same. You can, these operations commute. So you first take this quotient. This is not an algebra. So this is the quantization of mu inverse of 0. This is not an algebra, it's an A module. It should not be an algebra because mu inverse of 0 is not a Poisson manifold. So this is a module, but when we take H invariance, it actually has a natural algebra structure which descends from A. Anyway, this is the kind of general setting of quantum reduction, and now we try to implement this. What? Oh, I'm sorry. I forgot about the orbit. So this is in the case when O is 0. So I need to go back and correct everything. So so H acts on the symplectic manifold. This is mu inverse of O over H. And then we should have this and this. Now we wanted to quantize this, and it is cut out by the equation mu of M belongs to O. So we have this thing here. And well, maybe let me start with the case of 0 here, and then I will say what to change when we have O. So let's just do ordinary reduction for 0. That's not a twisted reduction. And so then everything is as I said. So this is 0. And now, if we replace 0 by orbit O inside G star, H star, what needs to be changed? Well, so we have mu inverse of O modulo H. So the equation mu of M equals to 0 is replaced by mu of M belongs to O. And we cut out, so the quotient by the ideal generated by this relation. So in quantum theory, what should we do? We should quantize the orbit O. So in the quantum mechanical setting, we need to find an ideal in the enveloping algebra which quantizes this orbit O so let me call this ideal I, so that U of G, U of H over I is a quantization of O. Well, this is in the case when H bar set to 1. And then I need to take And then I need to take quantum Hamiltonian reduction. I take A H modulo mu A times mu of I invariant H. So in the case O is 0, I is the augmentation ideal, which is the kernel of the map from U of G to C, and mu of I times U of G is the same thing as U of H times mu of H. A. Okay. And this reduces to the previous case. Okay, so yes. Yeah, that's a good point. I also missed that. So condition for quantum moment map, well, it should be that the differential, so the condition for the moment map classically was that the action, that it defines the action of the Lie algebra of H on M. And here it will be the same condition, namely that for any A in H, acting A is a bad letter because the algebra is A. Let me call it Z. For any Z in H, Z acting on A is the same thing as mu of Z commutator mu of Z acting on A. So here, commutator of mu of Z with A. And also mu is H invariant. So those are the conditions on the moment. So, so commutator is a quantum version of Poisson bracket. So the classical condition is that the action of a Lie algebra element on function A is the Poisson bracket of mu of Z with A. And this is obtained by quantizing this condition. Okay, so now try to implement it for the Hitchin system. And let's, for simplicity, start with the case without punctures. So the original setting that we were in. So, so we should take the algebra of differential operators on this huge infinite dimensional group G of C of t, which is a loop group. And then we should construct some, quantize some functions there. So quantum Hitchin system should be obtained from some two-sided invariant differential operators on this group G of K. So this is an infinite dimensional group, and there is actually quite a bit of technical trouble even talking about differential geometry on this group. But let me ignore that, because this can be done. This was done by Drinfeld, or something equivalent at least was done by them, and Beilinson. But let's pretend that G of k, let me call it L, because it's a loop group, is an ordinary Lie group. Then what are two-sided invariant differential operators on L? Well, so what are left invariant? So left invariant differential operators on the Lie group are well known to be identified with enveloping algebra of the Lie algebra of L. So now right action of G, when we do this, corresponds to the adjoint action on this enveloping algebra. So two-sided invariant this is the invariance in U of L with respect to L, which is simply the center of U of L. So we need to take some elements in the center of the universal enveloping algebra of the Lie algebra of our loop group. So what is this Lie algebra? So the Lie algebra of this group G of t, well, it's just the group of Laurent series with values in the Lie algebra of G. And so we need to take enveloping algebra of this. So what is the center? And so G is in this case simple. So what is the center of U of G of t? And then we get a disappointment. That the center is trivial. It's a disappointment. So this is in contrast with enveloping algebra of G itself, which has a big center, which has all the that would be even more disappointing. It's not that bad. So the center is trivial. Well, this Lie algebra is infinite dimensional, so you should really be talking about certain completions of enveloping algebra. And you might ask whether, so in fact need some completion, which I will maybe say a few words later about. But the bad news is, this is not going to help us. Center is still trivial. And I can explain what goes wrong. Well, our Hitchin Hamiltonian upstairs were defined by very simple formulas, in fact. And the question is, why can't we just lift those formulas in the quantum world? So let's remember about the quadratic Hamiltonian, so H2, classically. This is 1/2 of trace of phi squared, where phi is a Higgs field. So this lies in just G of Z. And so, so what is this? So if you write this phi as the summation of, let's say, phi n times z to the minus n, then this is going to be the sum of z to the n, and here is going to be the sum of over m, phi n minus n, if you like dz squared. And there will be a trace. So the trace means that I sum over some orthonormal basis. So so this phi n, so suppose we have some basis, so orthonormal basis ai of g, and phi is the summation of phi I times ai. And then, well, this is just 1/2 times the sum over n of z to the n and over I, phi mi times phi n minus m I. What? So let's see. Sum over m times that. So, well, this is a Higgs field on the formal punctured formal disk. So we have these things here. So we have z is just a parameter on this disk. But then, so in particular, we needed this to be invariant with respect to the action of the Lie algebra. So we want this phi pj with this h2 to be 0. But actually, if you do this commutator, you will find, so this is an infinite sum. And you will get ordering problem. There are factors here. And it won't be clear in which order to compute. And if you compute this on a highest weight representation, this is not going to make sense without ordering. So, but have infinite sums. And need ordering, normal ordering, as physicists say, to make it meaningful on finite dimensional representations. And then this commutation fails. This commutation relation fails. So that's a very instructive exercise to actually check that that's what happens. And so, in fact, this couldn't have succeeded. We were doomed to fail because Beilinson and Drinfeld showed so we would get, I mean, we worked on the open set of stable bundles, but in fact, our construction makes sense on the entire stack. There is a notion of differential operator on a stack, And then Beilinson and Drinfeld showed that if there is no punctures, then every globally defined differential operator on bond GX is a scalar. So this was doomed to fail. There is no quantization in this sense that I explained. However, we should recall something from physics to save the day. And what we should recall is that differential operators on a manifold is actually not the most natural. Differential operators acting on functions is actually not the most natural quantization of functions on the cotangent bundle. And the reason is, so recall from quantum mechanics, is that if you have M equals cotangent bundle of Y, we want quantization. So we want classical observables to quantize to operators on L2 of Y in quantum mechanics. But how do you define L2 of Y? Of course, if Y is a vector space, this is not a problem. We can just say these are L2 functions because we have a natural Lebesgue measure on Y. But to define it, need a Lebesgue, need to fix a measure on Y. And that's not natural because very often there won't be such a measure. I mean, we don't notice this when we do quantum mechanics on flat space, but we notice it once we do quantum mechanics on manifolds, which don't have a natural measure. But there is a way out, L2 of Y, with coefficients in so this is the bundle of densities to the power 1/2. So consider half densities of the form f of y times dy to the 1/2. Let's say this is a real manifold. And then there is a natural L2 structure, which is the integral of f of y absolute value squared times, this is going to get squared and become naturally a measure. So the most natural quantization from this point of view is differential operators on Y acting on the, in algebraic geometry, that would be 1/2 of the canonical bundle, 1/2 power of the canonical bundle. And in fact, it doesn't matter. So there are on some. So here we should recall what is twisted differential operators. So what is twisted differential operators? So if Y is a variety and L a line bundle on Y, then you can define the algebra D of YL of differential operators acting on sections of L. And you can check that this is not isomorphic in general to ordinary usual differential operators on Y. It's Morita equivalent to them, but not isomorphic. And in fact, so in fact, you can write formulas for this. And well, you can define d of y L to the n, and then you can check that formulas. So you can generate them by functions and vector fields, but in the relations, n will occur as a parameter. So the formulas, so it's generated by functions and vector fields, and the formula contains n as a parameter. So relations contain n as a parameter. So more precisely, locally, you pick a connection on L, and omega is the curvature of this connection. And then relations between functions and vector fields are the same as usual, but the only relation that changes, usually you have this relation that if you take covariant derivative with respect to vector field V, covariant derivative with respect to vector field U, and take commutator, this is covariant derivative of the Lie bracket of these vector fields. Okay, V bracket U. But here there will be another term which is omega of VU, which is a function. We substitute two vector fields into V and U. So this is what to twist the differential operators on L, and on L to the n, we just have to put n in front. And so this n can be replaced by any complex number. So can take n in C. And this is great because, of course, line bundle L to the n, where n is pi, for example, doesn't make any sense. But differential operator on this line bundle, which makes no sense, do make sense. In it, well, locally, there is a theorem that so for example, any bundle locally is trivial, so there is a connection on it. But then, of course, there is a gluing. So locally, you can even choose the connection to be flat. So locally, this algebra is going to be indistinguishable from usual differential operators. But the gluing maps is going to contain information about this bundle. Huh? Yeah. Like if you have a global connection on the bundle, for example. Suppose this is an affine variety. Then there is always a global connection. Because obstruction to constructing a connection lies in H1 in a coherent sheaf. And this vanishes on an affine variety. So in that case, this formula will give you the definition of algebra d of yl. Or d of yl to any power n, which is any complex numbers. I don't want to focus on this because this is not going to be very important. In the situation which we want, this k to the 1/2 will perfectly exist as a line bundle. So you should think about natural differential operators which naturally act on sections of line bundle rather than functions. Okay, so now, so in fact, so now we want, motivated by this, to replace d of Ban usual differential operators by d of Ban G with coefficients in k to the 1/2. And so how to do this? Well, we need to see how k to the 1/2. So can we obtain k to the 1/2 from some line bundle upstairs? So this means on the loop group. Well, do we have line bundles on loop groups? We're not, so on ordinary Lie groups, we don't have interesting line bundles because H2 of a Lie group is 0. However, on loop group, H2 is non-zero because H2 of the loop group by transgression is the same as H3 of the underlying group G, which is actually one-dimensional if G is simple. And therefore, there is an interesting line bundle on G of T. This is a line bundle is simply the central extension, which it's related to the central extension, which defines Kac-Moody algebra. So there is this Kac-Moody group, which is denoted by G hat, and it is included in the exact sequence C star G hat G of T 1. And line bundle. So this is a principal C star bundle. On G of T. And it is equivariant with respect to both left and right action because it comes from a central extension. So that's a central extension. So the Lie algebra of this group G hat is a affine Kac-Moody algebra, which is the form G of T plus C times K, and the commutator has the following form: A of T commutator with B of T is the usual Kac-Moody commutator, is the usual commutator, plus the residue at T equals 0 of A of T inner product with differential of B of T, where A and B lie here, and this gets multiplied by K. So this is the standard Kac-Moody extension, and then so this is principal C star bundle. Let me call it E, and the theorem is that K is obtained by a reduction downstairs of not of E, but of E to the power minus 2 H check, where this H check is the dual Coxeter number of the group G. So there is a number attached to every simple group G. For example, for the group E8, it is 30. So this means that in that case, the canonical bundle on band G is e to the minus 60. Okay, so this means that k to the 1/2. So now this means that if we want to obtain differential operators on k to the 1/2, we should consider not the usual enveloping algebra of G of T, but rather we should take the enveloping algebra of this affine Kac-Moody algebra, and we should mod out by the relation that this central element k equals to minus the dual Coxeter number. So we need to start with differential operators of G of T with the line bundle e to the minus h check, two-sided invariant, which is center of enveloping algebra of G hat modulo the relation K equals to minus the dual Coxer number. And then the center. And actually, we need to take some completion here. And then there is a theorem of Kazhdan and Frenkel, which is deep, pretty deep theorem. And it says that this does have a center. It is not trivial. And all Hitchin Hamiltonians Pi of phi lift to this center, which means they can be quantized. So what happens is you get something that is called a quantum anomaly in conformal field theory. So for k equals 0, you don't have center because you have that problem here with ordering. But there is so if you account for the ordering by taking normal ordering, you will get some what is called anomalies. But the anomalies will become they vanish. They will all come with a factor k plus h check. So so this is called that value of this k is called level, and this is called critical level, because Kac-Moody algebra representation theory behaves completely differently at this level due to the existence of this center. So so maybe let me explain what is going on with the quadratic element. But before that, I will formulate the theorem of Beilinson and Drinfeld. Which is proved in their still unpublished book. So, and it says that the image, the map, there is a the invariant, two-sided invariant differential operators on G of t acting on e to the minus h check. By the way, this is the only value of k for which this center is non-trivial. So that's the only thing you can do. So they descend to differential operators on bond G. And they cover the entire algebra. So this this map is surjective onto differential operators on bond G with coefficients in k to the 1/2. And this algebra, so this algebra is commutative, which is maybe surprising because differential operators normally are not commutative. But that's because we are considering global differential operators. If you want to think of an analogy or a special case of this, think about differential operators on an elliptic curve. So any differential operator on an elliptic curve, which is globally defined, will have constant coefficients, and therefore it will be just a polynomial of d over dz, where z is the additive coordinate. And similarly here, so this algebra is a polynomial algebra of g minus 1 times dimension of g, which is the dimension of Bahn generators, that quantizes the Hitchin system. And so in particular, in the case, well, all of this extends to the case of its punctures, except that surjectivity will not be true. There will be other differential operators. But never mind, the image is going to be a quantization of the Hitchin system always. And examples of this will include is the Gaudin system, and also elliptic Calogero-Moser, which means that I said that there was a problem with ordering there, but this will solve that problem for you. So if you compute systematically what happens to these Feigen-Frenkel central elements, which are actually not that easy to calculate, but for GLN it can be done, and compute their image, you will obtain the correct ordering, which will give you an integrable system. Yeah, well, there is no Dunkel you don't get, because Dunkel Weil group symmetry is not here. Put what condition? No, I don't know how to obtain Dunkel operators even for type A from this story. But in any case, Calogero-Moser will also, you will get many other examples. Affine Toda, you can quantize it for and many other examples. And then maybe the last thing I want to do is I want to explain so what happens to the quadratic operators in some explicit form, because it's related to something very important in representation theory and conformal field theory, which is called the Sugawara construction. So we have this classically 1/2 of trace of phi squared. And in quantum mechanical case, we should use, well, I'm going to call it T of z. Ti. Maybe let's take the Fourier mode. So there will be coefficients of this thing. So Tmn, they are going to be 1/2 the sum over m and over I, phi mi, phi n minus mi. But we should put a normal ordering, which will mean that bigger index first. So then this will make sense as a so this will make sense as an operator on highest weight representations. And then you can prove the following theorem. So this is called the Sugawara construction, which explains in detail what happened there when we failed to have commutativity. So if you commute phi p with Tn, this is going to be p times p times k plus h check times phi n plus p. So you see they commute only when k equals to minus h check. And also you can compute Tn with Tm, and then this is equal to k plus g, k plus h hat n minus m Tm plus n plus n q K plus H check, dimension of G, delta, and M. So you probably recognize the, so if you define Ln equals to Tn divided by K plus H check, then this, when K is different from H check with minus sign, then get Virasoro algebra representation with central element, which is this thing. So we divide it by K plus H squared, and we will get K times dimension of G over K plus H check. But at K equals to minus H check, this is central. And then there are these higher operators with cubic and higher, which come from higher central elements and which were constructed by Fagan and Frenkel. So Beilinson and Drinfeld used the Fagan-Frenkel theorem as an input, and with a lot of work, they were able to construct this quantum Hitchin system. Minus n, thank you. So I think I should stop here. Thank you very much.
Thank you. Are there any questions?
No, it's not. It is just Kalashov notation. But they occur in different contexts. Yes. Yeah, so when you do it, so I explained only this story for ordinary Hitchin system without punctures. So if you have punctures, then you have a way to twist the whole story. For every puncture, there is a twisting parameter. And so then you will obtain, so actually to get Garnier with parameters, or this Gaudin model, in full generality, you need this twisted story. And also to get Calogero-Moser, elliptic Calogero-Moser quantum, we also need this twisted story. So I think Nikita Nekrasov was planning to talk about some of this Calogero-Moser story, and probably he will revisit this topic.
Other questions?
I don't know how to describe it. I understood the question. He had this, in his Lux equations and algebraic curves, he had probably some generalization of Hitchin system, or how does this fit in the story?
I'm not sure. I have to, don't know enough about that. Yeah, maybe I should read about that. I should say that this is not, I'm not really an expert on this. So I was going to talk about quantum Hitchin system. So we started with L2 function. So I talked about differential operators acting on, twisted differential operator acting on L2 functions. So in fact, maybe I should mention what is analytic Langlands. This is just the spectral theory of the quantum Hitchin system acting on L2 of bond G of X, which we conveniently don't have to choose a measure because we're working with half densities. And so that's what we did with Frenkel and Kazhdan. So we define self-adjoint extensions of these operators. That uses some Hecke operators, but I didn't have time, unfortunately, to discuss that. And that's another piece of story which connects to number theory and to usual Langlands program. So, but maybe for some other time.
Yes. Okay, let us thank Pavel for, again, a wonderful set of lectures. We realized that people are getting a little bit tired. So after lunch, there will be one more talk by Eugene Zhang, and then there will be a movie. Okay?
But then there will be still...
And then there will be exercises and discussions.